So my name is Shami Chatterjee. I'm a senior researcher at Cornell University in the Department of Astronomy. So I'm an astronomer and I work with neutron stars. And off late, we've been moving in towards gravitational waves. And so we are building a low frequency gravitational wave detector, which is the size of our entire galaxy. My interest in astronomy, I guess, goes back all the way to my childhood. And even though I've taken a kind of twisty path to get to actually where I am, I think back on probably things like Carl Sagan's Cosmos as one of the earliest things I remember that got me really, really interested. That and Star Trek and the usual stories. That's where my interest in astronomy started. And then since then, I actually trained as an electrical engineer for my undergraduate degree, and then moved into applied physics and then into radio astronomy, which is actually really, really helps if you have a foot in the engineering camp and a foot in the astronomy camp, because that keeps you close to the instrumentation. So that's sort of my route into radio astronomy primarily, which is what I do. So a star is this massive ball of hydrogen that is being fused slowly to helium. And it's a delicate balance between these two irresistible forces. There's gravity that wants to pull everything in, and there's a thermonuclear explosion happening that wants to rip everything apart. And it's the balance between these two that keeps a star going. Now, as a star runs out of hydrogen to fuel itself, what happens is that gravity starts to win. And eventually, when a star has run out of all of its fuel, what will happen is that the star undergoes gravitational collapse. And then it explodes and blows its outer layers off in this cataclysmic explosion that's called a supernova. What's left behind at the core of the star can be one of three things. It can be white dwarfs, it can be neutron stars, or if there's nothing left behind, it can be a black hole. Now, which end state it ends up in depends on what the mass of the stellar core is just before the collapse happens. But if it is a neutron star, what we are talking about is an incredibly dense blob of matter. It's pure neutron matter. So a teaspoon of neutron star weighs about the same as Mount Everest. And we're talking about something which is 1.5 times the mass of our sun, but it's squeezed into something, not something smaller than the Earth, but something which is 10 kilometers in size, so something about the size of downtown San Francisco. It's a ball that's 1.5 times the mass of our sun, squeezed into something which is the size of downtown San Francisco, and it's spinning very, very rapidly. And that's a neutron star. And some of these neutron stars, the magnetic field happens to line up such that they produce this beam of emission, just like a lighthouse. And as they spin, if that beam from the lighthouse sweeps across our line of sight, every time it sweeps across, we see a blip. And that blip is basically the blip of a radio pulsar. And so this spinning neutron star, if its beam of emission crosses our line of sight, we can detect that as a radio pulsar. To understand what gravitational waves are, we need to take a step back and think about what gravity is. So we know Isaac Newton and the apple falling on his head, and he realizes that every object in the universe attracts every other object. And that was our understanding of gravitation all the way until Einstein. And Einstein comes up with this theory, which is general relativity. And general relativity, there's a bunch of equations, but the simple phrasing of general relativity is that matter tells space how to curve and space tells matter how to move. And so the way Einstein thought about gravity is that matter causes space-time to curve. And in that curved space-time, matter follows what is effectively a straight line, and that's how you end up with the sun, for example, curving the space-time in our solar system, and the Earth following that curvature and going into orbit around the sun. Now, anytime you have this, the way we like to make an analogy is like it's a rubber sheet and a bowling ball that's distorting the rubber sheet. Now, immediately the thought is, well, okay, can we push this analogy a little bit further? And Einstein's equations say, yes, you can push this a little bit further. You can have the rubber sheet oscillate. If you were to take two of these very, very massive bowling balls and spin them around each other on the rubber sheet, you get ripples in the rubber sheet and they propagate outwards. And these ripples in space-time are really what gravitational waves are. Now, this is a two-dimensional analogy and it just does not work for the real thing. The real thing, you actually have to get into the equations, but this is the understanding. It's ripples in the fabric of space-time itself, and that's what gravitational waves are. And this was a fundamental prediction of Einstein's theory of general relativity, and that's what we are testing with various observations. LIGO is the Laser Interferometric Gravitational Wave Observatory that's ground-based. In space, eventually we will be flying LISA, which is the Laser Interferometric Space Antenna, and that's going to be looking at somewhat longer wavelengths of gravitational waves. The study of gravitational waves is still in its infancy. So we are really at the stage of kind of just getting our hands on the technique. And it was 2015 when the first gravitational wave detector on the planet, the LIGO detectors, detected the in-spiral of two black holes. Now, this was stellar mass black holes. And so as these stellar mass black holes spiraled around each other, they produced these gravitational waves that coincidentally happened to sweep through the band that we hear in. So it swept through kilohertz wavelengths, and you can hear a little bloop of gravitational waves as these black holes in-spiraled around each other. LIGO is the first direct detection of gravitational waves. We have indirectly detected gravitational waves all the way back when we studied the in-spiral of binary neutron stars, and Hulse and Taylor detected the first binary pulsar, and they showed that that binary pulsar, the two neutron stars were orbiting around each other and they were losing energy at an exactly predictable rate that exactly matched Einstein's prediction from general relativity. And so for this indirect detection of gravitational waves, they got the Nobel Prize in 1995. In 2015 with LIGO, the detection is a direct detection of gravitational waves, also in this kilohertz regime, so millisecond gravitational waves. What we are working on now is a very long wavelength gravitational waves. So instead of stellar mass black holes spiraling around each other, we are now looking at supermassive black holes, billion solar mass black holes spiraling around each other. And so there, the period of these gravitational waves is years. And so the lengths of these gravitational waves are light years. And so you can imagine that a light year long gravitational wave is not something you can detect with a detector on Earth. Instead, we have to build a detector that is the size scale of our entire galaxy in order to be able to do this new kind of gravitational wave astronomy. So gravitational waves, just like electromagnetic waves, which have these different bands, there's optical wavelengths, longer wavelengths, which are radio, shorter wavelengths, which are ultraviolet or X-rays or gamma rays. Gravitational waves come across the full range of wavelengths as well. And so to be able to detect them, we need different techniques. When the gravitational wavelengths are of the order of kilometers, we can detect them with ground-based detectors, and that's what LIGO is. When they're significantly longer wavelength gravitational waves, we need space-based detectors. And LISA will fly in a few years, and that will be a space-based analog of LIGO, where it is basically these spacecraft flying in formation and directly looking for the deformation of space-time between the spacecrafts. Now, the kind of gravitational waves I'm interested in, which is produced by these supermassive black holes spiraling around each other, these are very long wavelength gravitational waves. These are light years long. And so you can't actually directly build a detector that will detect gravitational waves with those long wavelengths. Instead, what we do is we rely on these neutron stars, these radio pulsars, which are very, very, very precise clocks. And we treat the ticking of these clocks as marks on a meter scale. And so we're looking for these ticks of these clocks, and we're looking to see if some of these clocks suddenly speed up and some of these clocks suddenly slow down. And this correlated speeding up and slowing down of these clocks in different parts of the sky is what will allow us to detect the passage of a very long wavelength gravitational wave. So that's how we're building a galaxy-scale gravitational wave detector, by finding these pulsars, which are very, very precisely timable, and then timing them to very, very high precision, to precisions of the order of a few nanoseconds. And that's how we're going to be able to build this galaxy-scale gravitational wave detector. So while searching for these radio pulsars to build this galaxy-scale gravitational wave detector, we found some very, very interesting things in the radio sky. Now, the time domain radio sky is very poorly explored, and that's because of limitations in the telescopes and the techniques. Till now, we don't really know what the radio sky looks like in the time domain. So when we start looking, we find lots and lots of things that are of interest, things that go bump in the night and we go, wait, what was that? So one of the things that we've found are these things called fast radio bursts. And these are basically these millisecond blips of radio emission, which are swept in frequency. They arrive earlier at higher frequencies, later at lower frequencies, and they kind of sweep through our band of detection, and they last for a few milliseconds. And honestly, right now, we don't understand what produces them. That's what makes it an incredibly exciting topic, because we know we have localized one of these fast radio bursts. We know exactly where it's coming from, and we know that it is coming from a tiny dwarf galaxy, which is about 1 billion light years away. Right? So something which is a couple of billion light years away and yet can be detected by our radio telescopes. That means that when it was emitted, it was incredibly, astonishingly bright. Right? So something has to be incredibly energetic to be able to produce a beam of radio emission, a burst of radio emission that we can detect across galaxies. Radio telescopes, however, have very small fields of view on the sky. And so given the fact that radio telescopes see these tiny patches, and yet we've detected as many of these fast radio bursts as we have, we can then say, okay, how many of them must be popping off all over the sky? And when we do this calculation, we end up with some ridiculous numbers. We end up with 5 to 10,000 of these fast radio bursts are popping off all over the sky, somewhere at random, and they last for these milliseconds. Every single day, there's 5 to 10,000 of these popping off all over the sky. And so it's like the Earth is surrounded by some cosmic paparazzi. There's flash bulbs popping off all over. We just don't know where to be looking in order to be able to catch one of these millisecond flashes of radio waves. But we know that there's many of them, and we know that they correspond to something incredibly energetic. And that's what gets people very, very excited, that we have no idea what the mechanism is that is producing something that is so common in the universe and yet so incredibly energetic and so bright. And so we're chasing after these, and they're very, very exciting indeed. So all of this work that I'm talking about, we rely on all of these telescopes around the world. We rely on telescopes within the US, we rely on telescopes with our partners in Canada and all over the world, in Australia, in Europe, in India, in China. And these are all of these telescopes are run as public facilities. And in the US as well, especially, most of our telescopes are funded by the National Science Foundation. And it's basically our taxpayers who are funding all of this research, all of these telescopes, which are enabling us to find out absolutely fundamental things about the universe we live in. And so for that, we are very grateful to all of these agencies, and especially to all of the citizens and taxpayers who are supporting astronomy and science and all of these searches for meaning in the universe that we carry out.